welcome back, guys. We're going to finish up this review, and we'll go ahead and start with 39, number 39. So this was over probability, okay? This is dealing with odds. So the odds on, or if you recall, that means the odds against some event happening, are 4 to 5, okay? And so if you bet $16, how much are you going to win? Or how much are you going to gain? Well, the odds against something, guys, you're going to look at it like it's just a ratio, 5 to 4, okay? That ratio is the multiple by which you're going to win, okay? So all you really need to do is multiply this ratio by however much you bet, okay? So $16. And you multiply those two. Now, you can convert 5/4 into a decimal if you want, or you can just type all this into your calculator. If you do that, I think you're going to get $20. Okay. Oops, yeah. And the ratio of 20 to 16 is the same as 5 to 4. So you're going to win $20. And then, of course, you'll get your bet back. All right. Number 3 is just like it. Let's actually do number 3 real quick because so the odds against are 1 to 3. And if you bet $3 and you multiply these, the 3's would divide out and you're actually going to win $1, okay? And the reason is because the odds against this event happening are actually really quite low, okay? It's kind of the reverse from number 39. All right, let's look at 41. So a bag contains 4 red marbles, 3 blue marbles, and 7 green marbles. So if a marble is randomly selected, what's the probability that it's going to be blue? Well, to do this, you just figure out how many blue marbles there are. There's 3 of them, so that's going to go in your numerator. Over the total number of marbles, which appears to be 14. Okay. So this, if you recall, this we would be taking the theoretical approach here in quantifying the probability of this event. So it's 3/14, which is D. Number 42, it says on a multiple choice test, each question has 7 possible answers. If you make a random guess on the first question, what is the probability that you are correct? Well, only one question is going to be correct, and there's 7 possible answers, so it's going to be 1 out of 7, okay, or 1/7, in other words. Number 43. The probability that Louise will pass his statistics test is 0.69 or 69%. Find the probability that he will fail his statistics test. So this is, we're going to utilize that concept of a complement, okay? So if the probability that he passes is 0.69, then the probability that he fails will be 1 minus 0.69, which is, oops, I wrote 6.3, which is going to be 0.31, okay? So it's just, whatever probability is left, that's the probability that he will fail the exam. So 0.31. Okay, number 44. At a lumber company, shelves are sold in 5 types of wood, 3 different widths and 3 different lengths. Okay, how many different types of shelves could be ordered? So for this one, we're going to employ or utilize that multiplication principle, which said basically if you want to figure out the number of combinations, you multiply the number of ways each of these events could occur. So in other words, the number of ways you could pick the type of wood, which is 5, times the number of different widths times the number of different lengths. Okay, so you just multiply, and I think this is going to be 75. So there'll be a total of 75 different combinations there for shelving. All right, numbers 45 and 46 are just like 44. Okay, so that's why I'm going to skip those. We're going to come down here to number 47, and this will be taking us into chapter 8, 8a. So it says the population of a town is increasing by 642 people per year. State whether this growth is linear or exponential. And if the population is 1,700 today, what will the population be in 5 years? Well, guys, because the population of the town is increasing by a fixed amount, this is linear, okay? And it's going to be linear growth. And then to figure out what the population is going to be in 5 years, I'm going to remind you of that formula that I introduced. So the final population or amount, whatever it is that you're talking about, for linear growth is going to be equal to the initial times 1 plus the rate. Well, technically, remember, it's 1 plus or minus depending on whether it's growth or decay. The rate of growth times time, basically. In most cases, it's the number of years. Okay. So if we plug in here, the initial population is 1,700 times 1 plus the rate. Wait, am I doing this right? No, this is not quite right, guys. Hold on just a minute. We don't actually need this part right there. Okay. Yeah. We just need, because this is linear. It's the initial plus or minus, depending on whether it's growth or decay, the rate times time. All right, so the rate of growth is 642 people per year times, we're talking about 5 years. I'm not bothering to put the units, okay, because they would end up dividing out here, but 642 times 5, let's see, what is that? I want to say it's 520, but let's just be sure, shall we? Got stuff up from, I was grading your statistics projects and then having to input all of your data. Okay. Oh, well, it's off, 3,210. Then we're going to add this to the initial population, which is 1,700. We're going to get 4,910. 4,910. Okay. All right. So I think I'm trying to do one of each, guys. So this is an example of linear growth or decay. So remember this formula. Go back and look at your notes if you need to. Now the next one is going to deal with exponential. Okay. It says during the worst periods of hyperinflation, and boy, that's something that I never want to experience in my lifetime. In a certain country, the price of food increased at a rate of 30% per month. That's incredible. And this has happened before in other countries. It's never happened in the U.S. Okay. State whether this increase was linear or exponential. And then furthermore, if the food bill was $150 in 1 month during this period, what would it be in 3 months, 3 months later? Okay. So our interval of time here is not a year, rather it's a month. But because the rate of increase is a percentage, this is going to be exponential growth. Okay? So let me write that formula down. So it's going to be the final is equal to the initial times 1 plus or minus, depending on growth or decay, the rate, and then you're going to raise this to the power of time. So this one is the one that's just like the financial formula for finding compound interest. Okay, so the initial bill is $150 times 1 plus, the rate is 30%, but as a decimal that would be 0.30. And we're going to raise this to the third power because we're talking about 3 months. And let me just type all this into the calculator. So 150 times 1 plus 0.30. Close those parentheses, and let's raise this to the third power. We're going to get 3. That's pretty crazy, isn't it? $329.55. It says round to the nearest dollar, though. So to the nearest dollar, this 5 would bump that 9 up to a 10, which would make that 29 become 30. So $330. So that's just 3 months, guys. Think of what the food bill would cost after a year. So that's an example of hyperinflation. That's something hopefully we'll never have to experience. Okay, number 49. Now we'd be getting into chapter 9, okay, sections 9a and 9b. It says, write an equation for the linear function and use it to answer the given question. Round values to 2 decimal places. So it says Normal Town High School's pool record for the 100-yard freestyle was 47.3 seconds in 1990. Assume that the record falls at a constant rate of 0.07 seconds per year. What does the model predict for the record in the year 2007? So guys, if you remember, I introduced this formula, or this function, y equals mx plus b, okay, where m is the rate of, it could be either growth or decay, and then b is like your initial value, okay. Now notice they're using t for the independent variable, which is time, and they're using a capital R for the dependent variable, which is the actual record. Okay, so I've got x representing my independent variable time, and I have y over here representing my dependent variable for the record. Okay, so you can change those if you want, but like I've told you, in algebra classes, x and y are typically the default variables used, but I will go ahead and change these while I write this out. So the record is going to be equal to the rate, because it's falling, guys, it's negative 0.07, okay, times time, or the number of years, plus whatever the original record is, which is 47.3 seconds. Okay, so the 100-yard freestyle, if you know anything about swimming, in an Olympic-sized pool, that's up and back. Okay. All right, so this would be our model right here. Now the book likes to swap these two terms. They like to place the initial value first, and then the amount of change second. Okay, so just be aware of that. But once you know this, you can pretty much pick out the answer. It's got to be A. But to verify, to find the prediction for the record in 2007, well, that would be 17 years from 1990. 2007 minus 1990. is 17 years. Okay, so to actually evaluate this, or make a prediction, you'd plug in 17 years for time for your independent variable. You can plug all this into your calculator. It's negative 0.07. So the record is falling on average by 7/100ths of a second. That's what happens in these sporting events. We end up with 46.11 seconds. Okay, so like I said, if you can come up with the model first, then you basically will be able to pick out. You won't even have to substitute in for your independent variable. All right. Number 50 is just like the last one. Okay. And let's go to 51. All right, so the end is in sight here. So, but this is a good review, guys. It'll really get you ready for that final. Number 51 says, in the following situation, state whether the two variables are related in a way that might be described by a function, and if so, identify the independent and dependent variables. So this will kind of take us back to 8a. So we're taking a road trip in a car and want to know how far we've traveled. So we read the odometer at various times during the trip. Okay. Well, basically, one of our variables is distance, the distance that we've traveled. And then the other variable is going to be time. Okay. So if you think about this relationship, distance depends on time. Okay. If you want to know how far you've traveled, you need to know the time, how long you've spent driving. So the independent variable is going to be time, and the dependent variable is going to be the distance traveled. So this appears to be choice B. Okay. Number 52 is just like this one, guys. So I'm going to skip it, and we're going to look at the last one, 53. So this would be from 9b. It says, Crafty Bill's Cool Car Sales opened as a used car sales lot in 2001. And so if you look at this graph, that's kind of where it starts, right here, 2001. The graph shows the number of cars sold as a function of time, okay? So time is our independent variable, and the number of cars sold is our dependent variable. So the question is, what is the approximate number of cars sold in 2003? Well, before we answer this, first of all, look at the trend here. The number of sales is increasing every single year except for this period right here in which there's a decline in sales, okay? And that could be due to various factors. And then the number of sales continues to increase, okay? So it appears that this business is doing pretty well. But in 2003, you're just going to find 2003, find the point that corresponds to that. Kind of look over here. That's about halfway. So this would be 400, this would be 500. Halfway between 500 and 600 is about 550. So that's what I'm going to go with. Okay. So we're using the graph of this function, or of this relationship between these two variables, to figure out approximately what the number of car sales were in 2003. All right, guys. Well, that's it. I hope this video helps you out, and I hope you do well on the final. Okay. And I'll talk to you later.